for solving inequalities using addition or subtraction. You're going to see a lot of similarities in the steps that we used in section 3.4 with those that we learned back in the last chapter when we were solving equations using addition or subtraction. In that we can add to both sides or subtract the same number from both sides. But first we need to know a little bit more about what an inequality is, and so we start off with a definition. An inequality is a statement formed by placing an inequality symbol between two expressions. And as you can see, I have several inequality symbols that are listed there. We have the greater than, the less than, the greater than, the less than, the greater than or equal to, the less than or equal to. This one not so much. We don't use it a lot in solving inequalities. We do use this when we state restrictions later on for things such as rational functions and such. But that's more of an Algebra 1 or an Algebra 2 topic. All right, so let's define what a solution to an inequality is. Now notice here I have a singular solution, but typically with an inequality we have many solutions. A solution of an inequality with a variable is the set, notice plural here, meaning set of more than one answer, the set of all numbers that produce true statements when substituted in for the variable. See, this is an equation. This is last chapter, and earlier this chapter. This has one solution. X is 2. If you plug a 2 in for the x, you get 2 equals 2, true. No other number works. But this is an inequality with a greater than sign. This says x is greater than 2. There are lots of numbers greater than 2. I could substitute x for 3, or 10, or 1,000. There are infinitely many solutions to this inequality. And because of that, typically we represent solutions of inequalities by graphing the inequality on a number line. So let's go back to this guy. If I draw out a number line right here, and I'm not going to put a lot of points there, but I am going to put one in particular, my key value, which is 2. So this would be 3, this would be 4, 5, 1, and 0. I want all numbers greater than 2, but not equal to 2. So to represent that on a number line, because there are infinitely many numbers between any two numbers, I'm going to put an open circle around the 2. It's kind of like a barrier. It says you can't get to the 2. And since I want numbers greater than 2 means numbers to the right on the number line, I'm going to represent that by darkening this side and kind of shading it in and putting a big thick arrow here to indicate all numbers greater than 2. The circle says up to 2, but not including 2. Because, of course, 2 is not greater than 2. 2 is not a solution. Now, on these guys here that have the equal to part, the greater than or equal to, the less than or equal to, then we're going to want to include those numbers, and I'll show you what to do here in just a second. Now, this next example says x is less than 4. There are lots of numbers less than 4, too many to write down, so we represent it with a graph. So here's a number line drawn out for my use. I'm going to put 4 in the middle. And I want all values less than 4. Less than means smaller. It would be to the left. So an open circle around the 4 to represent not the 4 itself. And then I kind of shade in here. Put a big thick arrow there. And I shade in to the left to indicate all these numbers to this side. 2 and 3 and 3.5 and 3 3/4. And 0 and negative a million, negative a billion, and so on. All those are solutions to this guy. Now this next example, in fact the next two examples, have the inequality symbols with the equal to part. What we do there, and again our key value is -2. I'll put -2 in the middle, so this is -1, this is 0, this is -3, this is -4. I want all values greater than -2. That would be to the right of -2 on the number line, greater than. But I also want to include the -2 because it could be equal to -2. So I put the circle around the -2, but this time I shade it in. That represents that I want to include the -2 as part of the solution set. And then I'm going to shade to the right because it's greater than. Notice that when your inequality is written, if the variable is on the left side, the direction that the inequality arrow seems to be pointing is the side that you shade. See, this appears to be pointing to the right, I shade it to the right. This one's pointing to the right, I shade it to the right. This one was pointing to the left, I shade to the left. As long as the variable's on the left side, you can use that as a check. If the variable's on the right side, then it's just the opposite, as you might guess. Now in this case, this says m is less than or equal to 0. So 0 is my key value. I put some numbers in. You don't need to put a full number line with 30 or 40 numbers written down. 5 is plenty. M is less than or equal to 0. Less than means to the left. See how it's pointing to the left? But I want to include the 0, so instead of an open circle, I fill it in. And then I shade to the left. Okay? This is very important that you learn how to do this. This is stuff that you're going to see again and again in algebra. Now I'm going to reverse this. In this last example that I have written down, it says write an inequality represented by the graph. As you can see, it is greater than, but not equal to, negative 5. So I'm going to write x is greater than negative 5. I don't have the equal to because if this was filled in, then I would need it. It's not filled in, and therefore I just have the greater than symbol without the equal to. As I mentioned before, we solve inequalities very much like we solve equations. The key is to isolate the variable. And since these inequalities are going to be, that we're going to discuss in this section, involve adding and subtracting, we need properties just like we needed properties involving adding and subtracting when we were solving equations. And that's these right here. The addition and subtraction properties of inequalities. If A, B, and C are real numbers, then notice, if A is less than B, and this also works if it's an equal to, less than or equal to. If A is less than B, then A plus C is less than B plus C. You can add the same number to both sides of the inequality and it stays a less than. Or you can subtract the same number. A minus C is less than B minus C. So just like with equations, you can add the same number to both sides or subtract the same number from both sides. You can do that with a less than or equal to, and as it turns out, you can do that with a greater than or equal to. Part 2, if A is greater than B, then A plus C is greater than B plus C, adding C to both sides, and A minus C is greater than B minus C, subtracting C from both sides. So I have 6 examples, that I'm going to solve, and then once I get done solving it, I'm going to graph it on the number line like I was showing before. Now, we're going to isolate the variable. We're going to undo the stuff around the variable. Inverse operation, something, when you're adding 12, the inverse of adding 12 is to subtract 12. So I'm going to subtract 12 from both sides. I have to be careful here because of my signs. I get k is less than or equal to. Now remember, when you're subtracting a non-traditional subtraction problem, think of it as adding the opposite. Think of this as negative 4 plus negative 12. And that's negative 16. So I draw out my number line. I put negative 18, negative 17, negative 16, negative 15, negative 14, negative 13. That's plenty. I want less than or equal to negative 16. There's negative 16. The equal to means fill in the dot. We want that as part of our value, and then the less than means to the left. Again, since my variable is on the left side of my inequality in my answer, the direction that the arrow of the inequality sign appears to be pointing, it's not truly an arrow, but it looks that way, that's the side that we shade. This is pointing to the left, we shade to the left. Here, we have a 7 that's being added to n. It's not much different than this one. I'm going to subtract 7. I'll do a little shortcut this time. Again, I'm not crazy about this, but I will accept it. 3 and a negative 7 is a negative 4. So I draw out my number line here because that's my solution. I've isolated the variable. I'll put negative 4 in the middle. It's a little sloppy. Bear with me there. N is greater than, without the equal to, negative 4. So I put the open circle around the negative 4 open because there's no equal to include it. And it's pointing to the right. I want values greater than negative 4. I'm going to shade to the right, put the big arrow on the end like that. Now here's the first inequality we've come across where the variable was not on the left side. It's on the right side. Now you don't want to flip-flop the sides around because this is not an equation where you have that symmetric property. If you flip-flop the sides, you have to reverse the order of the inequality. But I'm going to leave it right where it sits. I'm going to subtract 4 from both sides to get rid of the plus 4. This is 6 greater than or equal to y. So when I go to graph, now this is my solution here, but when I go to graph this, notice it's not a big deal that the variable's on the right side. I'm going to put, let's see, 6 is my key value. I'm going to have the equal to, so I want to include the 6, but I'm not shading to the right. The inequality sign looks like it's pointing to the right, but my variable's on the right side. 6 is greater than or equal to y is the same as y is less than or equal to 6. See how the alligator mouth opens up to the bigger one. So I don't want greater than values. I don't want 7 and 8. 6 is not greater than or equal to 7 or greater than or equal to 8. I want the numbers in the other direction, on the other side. As I mentioned before, if the variable's on the right side instead of the left, it kind of reverses the whole process of what side to shade in. This looks like it's pointing in the right, but I shade to the left. Here's another one with the variable on the right side. I'm going to add 7 to both sides. -1 plus 7 is 6. I get 6 is greater than y. So it's a lot like the last problem. In fact, it even has the 6. It just doesn't have the equal to this time. So here's 4, 5, 6, 7, 8. I'm going to have an open circle around the 6 this time. And again, instead of shading to the right, like you might think because of the way it's pointing, the variable's on the right side, I shade to the left. I want values smaller. Now here's a third one in a row with the variable on the right side. I'm going to add 9 to both sides. To get rid of the -9, the variable has to be isolated. I got to get rid of the -9. -6 and +9 is 3 less than or equal to x. So I draw out my number line here to graph my solution. This is my answer right here, but the graph, I'll put below, my key value is 3. Now, because of the equal to, I want to include the 3, but I'm not shading to the left like you might think. X is over here on the right side, and you can see the alligator mouth opens up to the x, so we want values greater than this number here, 3. So I shade to the other side. I shade to the right, and I put the big arrow there. One more to go. This one's probably a little bit more like the first two because the variable's on the right side. I'll get rid of the -18 by adding 18 to both sides. See how similar it is to solving equations from the last chapter and from earlier on in this chapter? These cancel out. I get x is less than, looks like 53. Now here's another good reason why you don't start at 0 on the number line and put your values, because 53, that'd take forever. I'm going to put 53 right here. Here's 54, 55, 56, 52, 51, 50. That's probably a couple extra that I don't need, but I'll go ahead and write it this way. X is less than 53 means an open circle because there's no equal to, and because the variable's on the left side, I shade to the left here. It appears to be pointing. The values have to be less than 53, and a big arrow on the end. Now one last example. This is a little bit different than the ones that we've been doing. Most of your problems that you'll be working on will be like this. But here's a nice little example where it's kind of an application of what we're discussing. It says, write an inequality to represent that a golfer's longest drive is 325 yards. I'm going to let G represent the golfer's drive. Since the longest drive is 325, it can't be more than 325. It can be less, but it can't be more than. And it can't equal, because we had his longest drive being 325, so I'll put less than or equal 325, and that would be my answer. You'll get good at this, but you have to practice, practice, practice.